Welcome, dear friend, to this gentle journey through the fascinating world of computers and technology. As you settle into your comfortable space tonight, perhaps pulling your blanket a little closer, adjusting your pillow just right, I invite you to let the weight of your day slowly drift away. Whatever brought you here, whether it was a long day of work, study, or simply the desire for peaceful companionship as you prepare for sleep, know that you've found a quiet sanctuary where curiosity meets tranquility. Together, we'll explore 100 remarkable facts about computers, each one a small window into the extraordinary world of technology that surrounds us. Let these stories wash over you like gentle waves, carrying you deeper into relaxation with each passing moment. There's no need to remember everything you hear tonight. Simply let your mind wander through these digital landscapes, picking up whatever interests you while allowing the rest to fade into the soft background of approaching dreams. Take a deep breath now, feeling your chest rise and fall naturally, and as you exhale, release any remaining tension from your shoulders, your neck, your entire being. Before we begin our exploration, if you find comfort in these gentle journeys of discovery, consider leaving a quiet like or subscribing to join our peaceful community. Perhaps you'd like to share in the comments below where in the world you're listening from and what time it is as you prepare for rest. Your presence here creates a web of connection across time zones and continents, helping others who seek the same peaceful moments find their way to this calming space. But for now, simply relax and let yourself sink deeper into comfort. Let us begin our journey with the enchanting story of the very first computer bug, a tale that bridges the physical and digital worlds in the most unexpected way. On a warm September evening in 1947, computer pioneer Grace Hopper and her team were working on the Harvard Mark II computer when they encountered a malfunction. Upon investigation, they discovered an actual moth trapped between the relay contacts of the machine, its delicate wings causing the massive computer to malfunction. Hopper carefully removed the moth and taped it into the computer's logbook with the notation, "First actual case of bug being found." This whimsical moment gave us the term we still use today when something goes wrong with our computers. The preserved moth, with its fragile wings still visible, remains in the Smithsonian's National Museum of American History, a poetic reminder that even in our most sophisticated technologies, nature sometimes finds a way to leave its mark. This beautiful intersection of the natural and technological worlds shows us how language evolves from real experiences into metaphors that shape how we think about and interact with our digital companions. Moving deeper into the realm of early computing, consider the remarkable fact that the first computer programmer was a woman who lived in the 1800s, long before electronic computers existed. Ada Lovelace, daughter of the poet Lord Byron, possessed a unique combination of mathematical brilliance and poetic imagination. In 1843, she wrote the world's first computer algorithm, intended for Charles Babbage's analytical engine, a mechanical computer that was never fully built in her lifetime. What makes her contribution even more extraordinary is that she envisioned computers doing far more than simple calculations. She imagined machines that could compose music, create art, and engage with any form of symbolic representation. Her notes included the prophetic observation that machines might one day do anything that could be noted in symbols, from music to poetry to complex patterns. Ada saw beyond the brass gears and steam power of her era to imagine the creative potential of computing that we're only now beginning to fully realize. Her vision, written by candlelight in Victorian England, illuminates our modern digital age with its prescient understanding of what computers could become. The gentle hum of modern computers masks an almost incomprehensible speed of operation that deserves our quiet contemplation. Today's processors execute billions of operations every second, a pace so rapid that if you were to count from 1 to a billion at the rate of one number per second, without stopping for sleep, food, or rest, it would take you nearly 32 years to complete the task. Yet your computer processor accomplishes this feat multiple times in the span of a single heartbeat. Each operation involves electrons moving through circuits at speeds approaching the speed of light, choreographed in perfect synchronization to perform the calculations that power everything from simple text messages to complex scientific simulations. This invisible dance of electrons happens continuously, tirelessly, creating the digital experiences we've come to rely upon. The processor in your phone right now is performing more calculations each second than all of humanity could accomplish with pencil and paper in several lifetimes. Yet it does so silently, consuming less power than a small light bulb. Consider also the fascinating evolution of computer memory, which began with delay line memory that literally stored information as sound waves traveling through tubes of mercury. In the 1940s and early 50s, computers would send pulses of sound through these tubes, and the time it took for the sound to travel from one end to the other served as a form of temporary storage. The data existed only as vibrations moving through liquid metal, constantly circulating, constantly in motion. Engineers had to carefully control the temperature of the mercury because even small changes would alter the speed of sound and corrupt the data. This beautiful, almost musical form of memory storage reminds us that information can exist in many forms, not just as magnetic fields or electrical charges. The data literally sang through the mercury, creating a symphony of computation that our ancestors could almost hear. Today's solid-state memory seems almost mundane by comparison. Yet it carries forward the same essential purpose of holding our thoughts, our work, our memories in a form that can persist beyond the moment of their creation. In the gentle darkness of your room, you might notice the soft glow of LED lights from various devices. But did you know that the very first computer mouse, created by Douglas Engelbart in 1964, was carved from wood? This humble device, housed in a wooden case with metal wheels that tracked movement across a surface, revolutionized how we interact with computers. Engelbart called it a mouse, simply because the cord trailing from the back reminded him of a tail. This wooden mouse was part of a visionary demonstration in 1968, often called the mother of all demos, where Engelbart showed the world concepts that wouldn't become mainstream for decades, including video conferencing, collaborative editing, and hypertext. The warmth of wood under his hand as he moved this first mouse connected the natural world to the digital frontier in a tangible way. Today, billions of people use descendants of that wooden mouse, though now they're made of plastic and use optical sensors instead of wheels, and many have no tail at all, communicating wirelessly with their computers. The story of email begins earlier than many imagine, predating the widespread use of personal computers by many years. Ray Tomlinson sent the first email in 1971, choosing the @ symbol to separate the user name from the computer name, a convention we still use today. He can't remember what that first message said, describing it as something forgettable, perhaps just random keyboard characters like QWERTY. Yet this forgettable message marked the beginning of a communication revolution that would transform human interaction. The @ symbol itself, which had been used by merchants for centuries to denote "at the rate of," found new life in the digital age. This simple character, looking almost like a letter A wrapped in a protective embrace, became the universal symbol connecting billions of people across the globe. Every email address ever created honors Tomlinson's arbitrary but inspired choice, a reminder that sometimes the most profound innovations come from simple, practical decisions made without fanfare. Drifting deeper into computing history, we encounter the profound impact of the Apollo guidance computer, which took humanity to the moon with less processing power than a modern digital watch. This computer, weighing 70 pounds, had only 2 kilobytes of RAM and 36 kilobytes of fixed memory. The astronauts interfaced with it using a simple numeric keypad, entering 2-digit codes to execute programs. Yet, this humble machine performed the complex calculations necessary to navigate through space, land on the lunar surface, and return safely to Earth. The software was literally woven into the computer's memory, using core rope memory, where seamstresses threaded wires through magnetic cores to create permanent programs, earning it the nickname LOL memory, for little old lady memory, honoring the women who painstakingly assembled it. Each wire threaded through a core represented a 1, while wires bypassing cores represented zeros, creating software that was physically woven into the hardware like a technological tapestry. This beautiful fusion of textile craft and advanced technology carried humanity to another world. The Internet itself began as a modest network of just 4 computers in 1969, connected through phone lines in what was called ARPANET. The first message sent between these computers was supposed to be the word "log in," but the system crashed after transmitting just the letters LO, making the first Internet message an unintended but poetic lo, as in lo and behold. From these 4 computers at universities in California and Utah, the network has grown to connect billions of devices worldwide. Every second, this vast network carries approximately 150,000 gigabytes of data, enough to fill millions of books streaming through fiber optic cables that crisscross ocean floors and span continents. These cables, some no thicker than a garden hose, carry pulses of light that encode our messages, photos, videos, and dreams at speeds that would seem like magic to those who sent that first truncated message. The Internet, has become like a global nervous system, carrying thoughts and feelings across the planet faster than neurons fire in our own brains. Speaking of the brain, the comparison between computers and human cognition reveals fascinating parallels and differences. While a computer can perform calculations with perfect accuracy at incredible speeds, the human brain operates on just 20 watts of power, about the same as a dim light bulb. Yet it can recognize faces, understand language, create art, and experience emotions in ways that the most powerful supercomputers still struggle to replicate. Your brain contains approximately 86 billion neurons, each connecting to thousands of others, creating a network of such complexity that we're only beginning to understand its capabilities. Modern artificial intelligence systems attempting to mimic even simple brain functions require massive data centers consuming megawatts of power. The elegance of biological computation, refined over millions of years of evolution, remains a source of inspiration for computer scientists who dream of creating machines that can match the efficiency and adaptability of natural intelligence. Let's pause for a moment to appreciate the remarkable miniaturization that has occurred in computing technology. The ENIAC computer, built in 1946, weighed 30 tons, occupied 1,800 square feet, and used enough power to light a small neighborhood. Today, a smartphone that fits in your pocket has millions of times more processing power than ENIAC, yet uses so little energy it can run for days on a battery smaller than a deck of cards. This transformation follows Moore's law, observed by Gordon Moore in 1965, which predicted that the number of transistors on a chip would double approximately every 2 years, while the cost would halve. This exponential growth has continued for decades, giving us devices of almost unimaginable capability. A single modern processor chip contains billions of transistors, each one smaller than a virus, switching on and off billions of times per second in perfect coordination. If these transistors were the size of grains of rice, a modern processor would cover several city blocks, yet they all fit on a chip smaller than your fingernail. The story of computer graphics began with simple dots of light on oscilloscope screens, where early programmers created the first computer game, Tennis for Two, in 1958. This game, played on an oscilloscope at Brookhaven National Laboratory, displayed a simple side view of a tennis court with a bouncing ball affected by gravity. Players used aluminum controllers to hit the ball back and forth, watching the green phosphor trail trace its arc across the screen. From these humble beginnings of glowing dots, computer graphics evolved to create entire virtual worlds indistinguishable from reality. Modern graphics cards perform trillions of calculations per second to render realistic lighting, shadows, reflections, and textures. Each frame of a modern video game requires calculating the behavior of millions of polygons, the physics of particle systems, and the interaction of light with surfaces, all completed in less than a 60th of a second to maintain smooth motion. Before we continue deeper into our journey, if you're finding peace in these gentle explorations of technology's wonders, remember that a simple like helps others discover this calm space too, creating ripples of tranquility across the digital landscape. The development of the hard drive offers another fascinating chapter in computing history. The first commercial hard drive, IBM's RAMAC 305, was introduced in 1956. It was the size of 2 refrigerators, weighed over a ton, and could store 5 megabytes of data. Airlines leased these massive machines for $63,000 per year in today's currency to manage reservations. Compare this to modern drives that can store 20 terabytes in a device the size of a paperback book, representing a 4 million-fold increase in storage density. If cars had improved at the same rate as hard drives, a modern car would be able to travel at the speed of light, cost less than a penny, and fit millions of them on the head of a pin. The magnetic surfaces of these drives spin at speeds up to 15,000 revolutions per minute, with red right heads floating above them on a cushion of air thinner than a strand of DNA, never touching the surface yet reading and writing billions of bits of data with perfect precision. The world of computer programming has given us languages with wonderfully expressive names that hint at their purposes and philosophies. Python was named not after the snake, but after Monty Python's Flying Circus, reflecting its creator's desire to make programming fun. Java was almost called Oak after a tree outside the programmer's window, but that name was already taken, so they named it after coffee, which fueled their long coding sessions. The language C was named simply because it came after B, which itself was derived from BCPL. Ruby was chosen to reflect the language's beauty and value, while Perl originally stood for practical extraction and report language, but was retroactively redefined as pathologically eclectic rubbish lister by its own creator in a moment of self-deprecating humor. These names remind us that behind every line of code are human beings with senses of humor, aesthetic preferences, and the very human tendency to name things after what inspires or amuses them. The concept of computer viruses emerged from thought experiments before becoming digital reality. In 1949, mathematician John von Neumann theorized about self-replicating programs, describing machines that could reproduce themselves. The first computer virus created as an experiment was called Creeper in 1971, which displayed the message, "I'm the creeper, catch me if you can," as it jumped from computer to computer on ARPANET. In response, the first antivirus program, called Reaper, was created to chase down and delete Creeper, beginning an endless game of digital cat and mouse that continues today. Modern malware has evolved far beyond these playful beginnings, yet the fundamental concept remains the same. Programs that copy themselves and spread from host to host, like biological viruses jumping between cells. The parallel between biological and computer viruses is so strong that researchers study the spread of computer infections using the same epidemiological models used for biological diseases. Consider the remarkable fact that all digital information, every photo, song, video, and document ultimately exists as patterns of ones and zeros, presence and absence, on and off. This binary foundation means that at the deepest level, a symphony by Mozart and a photograph of a sunset are made of the same fundamental building blocks, just arranged in different patterns. A single high-resolution photograph contains millions of these binary digits, each one contributing to the final image like individual brushstrokes in a pointillist painting. When you send a text message, your words are converted into binary, transmitted as pulses of electromagnetic energy, and reconstructed on the other side, a process that happens so quickly and reliably that we rarely pause to appreciate its elegance. This universal language of binary allows any type of information to be stored, transmitted, and processed by computers, creating a kind of digital alchemy that transforms human expression into patterns of electrical signals and back again. The development of the transistor in 1947 at Bell Laboratories changed the trajectory of human civilization. This tiny device, originally the size of a thumb, could amplify and switch electronic signals without the heat and bulk of vacuum tubes. The first transistor was made from a paper clip, gold foil, and a germanium crystal, assembled on a workbench in what seemed like a modest experiment. Yet from this humble beginning came the foundation for all modern electronics. Today's computer chips contain transistors so small that you could fit millions of them on the period at the end of this sentence. These transistors are manufactured using processes that manipulate matter at nearly the atomic level, with features smaller than the wavelength of visible light. The machines that create these chips operate in clean rooms where the air is thousands of times purer than a hospital operating room, where a single speck of dust could ruin millions of transistors. The story of Wi-Fi technology includes an unexpected connection to Hollywood glamour. The frequency-hopping spread-spectrum technology that makes Wi-Fi possible was co-invented by actress Hedy Lamarr and composer George Antheil in 1942. Lamarr, who was also a self-taught inventor, developed this technology to help Allied torpedoes avoid being jammed by the enemy during World War II. Their system used a piano roll to randomly change radio frequencies, making it impossible for enemies to jam the signal. Though the military didn't adopt their specific system during the war, the principle they developed became fundamental to modern wireless communication. Every time you connect to Wi-Fi, you're using a descendant of the technology conceived by a Hollywood actress who did her inventing between film shoots. Lamarr never profited from her invention, but she was finally recognized for her contributions to technology shortly before her death, a reminder that innovation can come from the most unexpected sources. The physical infrastructure of the Internet includes underwater cables that are vulnerable to some surprising threats. Sharks occasionally bite these fiber optic cables, possibly attracted to the electromagnetic fields they emit. To protect against this, modern cables are wrapped in special protective layers, essentially armor against curious marine life. These cables carry 99% of international data traffic, lying on ocean floors at depths where pressure would crush a human body in seconds. When you send a message to someone on another continent, it likely travels through these submarine cables, racing through glass fibers as pulses of light, perhaps passing by sleeping whales or ancient shipwrecks. The route your data takes is determined in milliseconds by routers that calculate the fastest path through this underwater web. adapting instantly to cable failures or network congestion. This hidden ocean network is the circulatory system of our global digital civilization, vulnerable yet resilient, carrying our collective communications through the silent depths. Computer keyboards carry forward a legacy from the age of mechanical typewriters. The QWERTY layout we use today was designed in the 1870s to prevent typewriter jams by placing commonly used letter pairs apart from each other, slowing down typing just enough to keep the mechanical arms from tangling. This layout became so entrenched that even though the mechanical constraints disappeared with electric typewriters and then computers, we continue using an arrangement designed to slow us down. Alternative layouts like Dvorak, scientifically designed for efficiency and comfort, have been proven to be faster and cause less strain. Yet QWERTY persists, a testament to the power of established standards. Every time you type, your fingers dance across a pattern frozen in time from the Victorian era, a technological fossil embedded in our most modern devices. This persistence of old solutions in new contexts appears throughout computing, where decisions made decades ago continue to shape our daily digital interactions. The cooling systems in data centers have evolved into marvels of engineering efficiency. Some data centers are now built in cold climates or even underwater to take advantage of natural cooling. Microsoft has experimented with underwater data centers in Project Natick, placing sealed containers full of servers on the ocean floor, where the cold water naturally dissipates heat. Facebook built a data center near the Arctic Circle in Sweden, using the frigid air to cool servers that help billions of people share photos and messages. These servers generate so much heat that some facilities use it to warm nearby buildings, turning waste into resource. The sound of cooling fans in data centers creates a constant white noise that technicians describe as oddly soothing, like mechanical rain. Some data centers use as much electricity as small cities, yet they're becoming increasingly efficient, finding creative ways to reduce their environmental impact while managing the ever-growing demand for computation and storage. The development of computer memory includes a fascinating chapter about magnetic core memory, which was literally woven by hand. In the 1950s and 60s, workers, mostly women with experience in textile mills, threaded thin wires through tiny magnetic rings called cores. Each core could store a single bit of information based on its magnetic polarity. These memory planes looked like technological quilts with thousands of cores arranged in grids, each one carefully strung with sense and inhibit wires. The work required incredible patience and precision, as a single misthreaded wire could corrupt data. Unlike modern RAM, core memory was non-volatile, meaning it retained information even when power was lost. Apollo spacecraft carried core memory to the moon, trusting these hand-woven matrices with the lives of astronauts. The transition from core memory to semiconductor memory marked the end of this beautiful fusion of craftsmanship and technology, though the term core dump for a complete memory printout preserves the language from this era. The world's first computer password was remarkably simple and remarkably ineffective. When passwords were introduced at MIT in 1961, they were stored in plain text where anyone could read them. The first password was simply password, setting a tradition of poor security choices that continues today. Despite decades of security education, password and 123456 remain among the most common passwords globally. Modern password requirements, demanding combinations of uppercase, lowercase, numbers, and special characters, arose from a government employee's personal preferences in 2003, not from scientific study. Research now shows that long passphrases made of random common words are both more secure and easier to remember than complex passwords with special characters. The humble password, our first line of digital defense, reveals the perpetual tension between security and convenience, between what we know we should do and what we actually do in our tired, hurried moments. Consider the remarkable journey of computer displays from monochrome text to vibrant millions of colors. Early computer monitors displayed only green or amber text on black backgrounds, the phosphor coating inside cathode ray tubes glowing with a distinctive hue that many remember with nostalgia. The IBM PC's CGA graphics in 1981 offered just 4 colors at once from a palette of 16, creating a distinctive aesthetic of cyan, magenta, white, and black that defined early computer games. Today's displays can show over 16 million distinct colors, more than the human eye can actually distinguish. Each pixel on a modern 4K display contains subpixels of red, green, and blue that combine in different intensities to create any color imaginable. OLED displays generate their own light at the pixel level, allowing for perfect blacks by simply turning off pixels entirely. The engineering required to control millions of pixels, refreshing them 60 or more times per second, happens invisibly behind the smooth glass surfaces we touch and gaze at daily. The concept of cloud computing returns us to an older model of computing in an unexpected way. In the early days, computers were so expensive that organizations used time-sharing systems where many users would connect to a single powerful computer through terminals. Personal computers moved processing power to individual desks, but cloud computing has swung the pendulum back, centralizing computation in massive data centers, while our devices act as sophisticated terminals. The term cloud itself was borrowed from network diagrams where the internet was represented as a cloud shape to indicate a complex system whose internal workings didn't need to be understood by users. There is no cloud, just other people's computers, as the saying goes, yet this abstraction has transformed how we think about data and computation. Your photos, documents, and messages exist in multiple copies across different data centers, automatically synchronized and backed up, creating a kind of digital immortality for our information. The surprising connection between gaming and scientific advancement reveals how play drives innovation. Graphics processing units, or GPUs, were originally designed to render complex, three-dimensional game worlds, but scientists discovered these chips were perfect for parallel processing tasks. Today, GPUs power artificial intelligence research, weather forecasting, and drug discovery. Protein folding simulations that help develop new medicines run on the same type of chips that render dragon scales and explosive effects in video games. The massive parallel processing power needed to calculate realistic water physics in games turns out to be perfect for modeling climate change. Gamers unknowingly funded the development of hardware that now drives scientific breakthroughs. Some researchers even embed scientific problems into games, allowing players to contribute to research while they play. This beautiful convergence of entertainment and discovery shows how human curiosity and desire for play can advance our understanding of the universe. The phenomenon of cryptocurrency mining has created some unusual situations around the world. In some regions, the heat generated by mining computers is used to grow tomatoes in greenhouses or warm swimming pools. One creative miner in Siberia heats his entire house with the waste heat from his mining operation, essentially getting paid to stay warm through the long winter. The global Bitcoin network uses more electricity than entire countries like Argentina or Norway, yet proposals exist to use this computation for useful work beyond securing transactions. The relationship between computation and energy has become so direct that you can literally convert electricity into digital currency, a form of alchemy that would have seemed like magic to previous generations. Some abandoned factories and power plants have been converted into mining facilities, bringing digital life to industrial ruins. The evolution of computer storage tells a story of exponential growth that's difficult to comprehend. In 1956, IBM's RAMAC computer needed 50 24-inch disks to store 5 megabytes. Today, a micro SD card smaller than a fingernail can hold 1 terabyte, 200,000 times more storage in a space millions of times smaller. If books had undergone similar miniaturization, you could fit every book ever written onto something the size of a postage stamp. This transformation has changed how we relate to information. We no longer need to carefully choose what to keep. We can record everything. Some people now have their entire lives documented in photos and videos, creating personal archives that would have been impossible for even royalty in previous centuries. Yet this abundance creates its own challenges as we struggle to find meaningful memories in oceans of data. Computer processors generate patterns of heat that can be visualized with thermal cameras, creating abstract art from computation. Each calculation produces a tiny amount of heat, and different types of operations create different thermal signatures. Watching a processor work through thermal imaging is like seeing thought itself rendered visible, with hotspots blooming and fading as the chip switches between tasks. Overclockers, enthusiasts who push processors beyond their rated speeds, study these thermal patterns obsessively, using liquid nitrogen or even liquid helium to cool chips to hundreds of degrees below zero, allowing them to run at speeds that would instantly destroy them at room temperature. The quest for computational speed has led to some processors being cooled to temperatures colder than outer space, pushing silicon to its absolute limits. The Internet has developed its own geography, with data flowing along specific routes like digital trade winds. Content delivery networks cache popular videos and websites at strategic locations. So when you watch a video, it likely comes from a server in your own city, rather than traveling across oceans. These networks create a hidden topology where physical distance matters less than network distance. Two buildings next to each other might have their internet traffic routed through servers thousands of miles apart before connecting. Internet exchange points, physical locations where different networks connect, have become some of the most important yet anonymous buildings in modern cities. A single building in Frankfurt carries more internet traffic than entire countries, yet most people walk past it without knowing its significance. The story of the computer virus, known as Stuxnet, reads like a technological thriller. Discovered in 2010, this sophisticated malware was designed to damage specific industrial equipment in nuclear facilities. It spread through USB drives, infected computers worldwide while searching for its specific target, then caused centrifuges to spin out of control while reporting normal operations to monitoring systems. This virus was so complex that it exploited 4 different previously unknown Windows vulnerabilities and included a valid digital certificate to appear legitimate. Stuxnet marked a new era of cyber warfare, where code could cause physical destruction. The virus contained references to biblical stories and executed its payload with mathematical precision, a combination of mysticism and technology that seems almost like science fiction. Computer random number generators face a philosophical challenge, because computers, being deterministic machines, cannot generate truly random numbers. Instead, they use pseudo-random number generators that produce sequences of numbers that appear random but are actually generated by mathematical formulas. For true randomness, computers must look to the physical world, measuring radioactive decay, atmospheric noise, or even lava lamps. One company uses a wall of 100 lava lamps filmed by cameras to generate random numbers, the unpredictable bubbling of heated wax providing entropy for encryption keys that protect internet traffic. This beautiful solution connects the analog chaos of the physical world to the digital precision of computers. Every secure connection you make online might be protected by the random dance of colored wax in a lamp, a poetic intersection of the psychedelic 60s and modern cryptography. The development of quantum computers represents a fundamental shift in how we think about computation. While classical computers use bits that are either 0 or 1, quantum computers use quantum bits, or qubits, that can exist in a superposition of both states simultaneously. This allows quantum computers to explore multiple solutions to a problem at once, potentially solving certain types of problems exponentially faster than classical computers. These machines must be cooled to temperatures approaching absolute zero, colder than deep space, to maintain quantum coherence. The interior of a quantum computer looks more like an art installation than traditional computing equipment, with golden chambers and intricate wiring creating a chandelier of exotic technology. Scientists describe programming quantum computers as more like composing music than writing traditional code, requiring an intuitive understanding of quantum harmonics and interference patterns. The humble USB connector has a curious property that seems to defy probability. Despite having only two possible orientations, many people report needing 3 attempts to plug in a USB cable correctly. This phenomenon, jokingly called USB superposition, suggests that USB connectors exist in a quantum state until observed. The USB standard has evolved through multiple versions, yet maintained backward compatibility, allowing devices from different decades to communicate. The USB Implementers Forum, which oversees the standard, consists of over 700 companies working together to ensure your keyboard, mouse, phone, and countless other devices can all connect using the same type of port. This remarkable cooperation between competitors has created one of the most successful technology standards in history. Computer facial recognition has revealed that humans have consistent biases in how we perceive faces. The algorithms, trained on human-labeled data, inherited our prejudices and amplified them, forcing us to confront uncomfortable truths about perception and bias. This led to important conversations about fairness in artificial intelligence and the need for diverse training data. Some facial recognition systems can now identify individuals from partial faces, gait patterns, or even the pattern of veins in their hands. Yet these same systems can be fooled by specially designed glasses or makeup patterns that exploit weaknesses in their algorithms. The cat and mouse game between recognition systems and those seeking to evade them has created a new form of digital camouflage, where fashion meets privacy protection. The energy efficiency of biological systems continues to inspire computer scientists. A single E. coli bacterium performs about 1 billion operations per second, while consuming only about a picowatt of power, making it roughly 1 million times more energy efficient than the most efficient computer processors. DNA itself is an incredibly dense storage medium, capable of storing 215 petabytes of data in a single gram. Scientists have successfully stored books, images, and even movies in synthetic DNA, creating archives that could last thousands of years. The idea of biological computers, using living cells or biochemical reactions for computation, moves from science fiction toward reality as researchers explore ways to harness the computational power that already exists in nature. Consider the remarkable fact that every smartphone contains elements from almost every corner of the periodic table. Rare earth elements with exotic names like yttrium, lanthanum, and europium give your screen its colors and your speakers their magnetism. Tantalum from Africa, lithium from South America, and dozens of other elements combine in a device that fits in your pocket. The global supply chain required to build a single phone spans continents and involves hundreds of thousands of people, from miners to engineers to assembly workers. When you hold your phone, you hold a piece of almost every continent, a crystallization of global human cooperation and trade. The recycling of old phones has become a form of urban mining, extracting valuable elements from discarded devices rather than from the earth. Computer algorithms have developed their own aesthetic preferences, sometimes creating art that surprises their programmers. Neural networks, trained on thousands of paintings, can generate new artworks that feel authentic yet unprecedented. These systems don't just mimic, they interpolate and extrapolate, finding patterns humans never noticed. Some AI-generated artworks have sold for hundreds of thousands of dollars at auction, raising questions about creativity, authorship, and the nature of art itself. Musicians use AI to explore new compositions. Writers use it to overcome creative blocks, and artists use it to visualize impossible worlds. The collaboration between human creativity and machine learning creates a new form of cyborg art, where the boundary between human and artificial creativity becomes increasingly blurred. The infrastructure of the Internet includes some wonderfully analog components. Internet backbone routers, handling millions of connections, still use cooling fans that need regular oiling. Fiber optic cables are vulnerable to backhoes, leading to the phrase backhoe fade for internet outages caused by construction accidents. In 2008, damage to underwater cables in the Mediterranean slowed internet speeds for millions of people across the Middle East and India, showing how physical vulnerabilities affect our digital world. Repair ships constantly patrol the oceans, ready to fix cable breaks using specialized equipment that can work at depths where water pressure exceeds 1,000 atmospheres. These ships carry spare cable measured in thousands of kilometers, ready to splice new sections into breaks caused by earthquakes, anchors, or curious marine life. The development of solid-state drives represents a return to silence in computing. After decades of clicking, whirring hard drives, SSDs brought quiet storage with no moving parts. This transition from mechanical to solid-state storage eliminated one of the last moving parts in computers, creating machines that operate in perfect silence except for cooling fans. The absence of mechanical delay makes computers feel more responsive, more alive, even though they have actually become more still. This paradox, where less movement creates a greater sense of activity, reflects how our perception of speed relates more to responsiveness than actual motion. Some people miss the sound of hard drives, the gentle clicking that provided auditory feedback of computer activity. There are now apps that simulate these sounds for nostalgic users who find the silence unsettling. The story of computer typography involves a calligrapher, a college dropout, and a revolution in how we see text. Steve Jobs audited a calligraphy class after dropping out of Reed College, learning about serif and sans serif fonts, spacing, and what makes typography beautiful. Years later, he insisted the first Macintosh include multiple fonts, making it the first computer designed with typography in mind. This decision transformed computers from machines that displayed text to machines that displayed beautiful text. Today, web fonts allow designers to use thousands of different typefaces, each one carefully crafted to convey different emotions and meanings. The curves of each letter are defined by mathematical equations called Bézier curves, named after French engineer Pierre Bézier, who developed them for car design, but found immortality in how computers draw letters. The principle of error correction in computers mirrors biological DNA repair mechanisms. Just as our cells constantly check and repair DNA damage, computers use error-correcting codes to ensure data integrity. These codes add redundant information that allows systems to detect and fix errors caused by cosmic rays, electrical interference, or component degradation. Without error correction, a single flipped bit could crash programs or corrupt files. Modern memory modules include error correction that fixes single-bit errors and detects double-bit errors, silently protecting our data from the random chaos of the physical world. This invisible safety net operates continuously, fixing thousands of errors you never know occurred, maintaining the illusion of perfect digital reliability in an imperfect physical universe. Computer networks exhibit emergent behaviors that remind us of biological systems. Network congestion spreads like disease. Packets route around damage, like ants finding new paths. And distributed systems achieve consensus like flocks of birds choosing direction. The Internet Protocol Suite, TCP/IP, was designed to survive nuclear war, routing around destroyed nodes automatically. This resilience comes from simplicity. Each router only needs to know about its immediate neighbors, yet together they create a global communication system. When you send a message across the world, no single computer knows the complete path it will take. Instead, each router makes local decisions that collectively guide your data to its destination, like a vast game of telephone that somehow maintains perfect fidelity. The relationship between gaming and military technology has deep roots. The first flight simulators were analog computers that used mechanical linkages to model aircraft behavior. The military's need for realistic training simulations drove advances in computer graphics that later appeared in video games. Today's game engines are used to train soldiers, plan military operations, and even treat post-traumatic stress disorder through controlled virtual exposure therapy. The same technology that creates fantasy worlds helps pilots learn to fly, surgeons practice operations, and architects walk through buildings before they're built. This dual use of technology for entertainment and training shows how play and preparation share common ground in the human experience. Modern processors contain billions of transistors arranged in intricate patterns that look like alien cities when viewed under electron microscopes. The manufacturing process involves hundreds of steps, using light wavelengths smaller than visible spectrum to etch features onto silicon wafers. A single dust particle can ruin millions of transistors, so chip fabrication facilities maintain cleanliness standards stricter than surgical operating rooms. The machines that make these chips cost hundreds of millions of dollars and require teams of specialists to operate. Only a handful of facilities worldwide can produce the most advanced processors, making them strategic resources as important as oil or rare minerals. The knowledge required to build these chips represents one of humanity's most complex technical achievements, requiring expertise in physics, chemistry, materials science, and engineering. The concept of digital twins creates virtual copies of physical objects that exist in computer simulations. Engineers use digital twins of jet engines to predict maintenance needs, monitoring virtual engines that experience every flight, every temperature change, every stress their physical counterparts endure. Cities create digital twins to simulate traffic patterns, emergency responses, and infrastructure changes before implementing them in reality. Even human organs have digital twins, allowing doctors to test treatments on virtual hearts or livers before operating on patients. These simulations become increasingly sophisticated, incorporating real-time data from sensors to maintain perfect synchronization with their physical twins. The boundary between simulation and reality blurs as digital twins become more accurate, raising philosophical questions about the nature of existence and experience. Computer security researchers have discovered that processors leak information through unexpected channels. The sounds computers make, the patterns of power consumption, even the electromagnetic radiation they emit can reveal what they're processing. Researchers have extracted encryption keys by listening to the high-pitched whine of capacitors, reading data from the reflections on eyeglasses in video calls, and stealing passwords by measuring tiny voltage fluctuations. These side-channel attacks reveal that information wants to escape, finding paths through the physical world that bypass digital security. The quest for perfect security becomes a game of plugging increasingly subtle leaks, securing not just the digital realm, but the physical emanations of computation. The preservation of digital information faces a paradox where older storage methods often last longer than newer ones. Stone tablets last millennia, paper centuries, magnetic tape decades, but modern flash storage might corrupt in just years without power. Digital archaeologists work to recover data from obsolete formats, maintaining museums of old hardware to read forgotten media. The rapid pace of technological change means file formats become unreadable within decades, creating a digital dark age where recent history becomes inaccessible. Projects like the Internet Archive work to preserve our digital heritage, taking snapshots of the entire web, saving billions of pages that might otherwise disappear. The challenge of digital preservation reminds us that permanence requires active maintenance, that memory needs constant renewal to persist. The development of artificial intelligence has revealed unexpected truths about human intelligence. Tasks we thought were hard, like chess or mathematics, proved relatively easy for computers, while tasks we thought were simple, like recognizing a cat or understanding a joke, proved extraordinarily difficult. This paradox, known as Moravec's paradox, shows that millions of years of evolution have optimized our brains for tasks we don't even realize are complex. A child can easily stack blocks, recognize faces, and understand stories, capabilities that require massive computational power to simulate. This humbling realization has shifted AI research toward appreciating the sophistication of basic perception and motor control, recognizing that intelligence isn't just about logic, but about navigating the messy, ambiguous physical world. Computer modeling of climate systems represents one of humanity's most ambitious attempts to predict the future. These models divide Earth's atmosphere, oceans, and land into millions of cells, calculating how energy and matter flow between them. Supercomputers run these simulations continuously, exploring different scenarios, trying to understand how small changes might cascade into global effects. The butterfly effect, where tiny changes can have massive consequences, makes perfect prediction impossible. Yet, patterns emerge from the chaos. These models require so much computation that climate scientists must carefully choose which questions to ask, which scenarios to explore. The future of human civilization might depend on the accuracy of these silicon prophecies, mathematical crystal balls gazing into our planet's destiny. The strange world of esports has created professional athletes who compete sitting down, earning millions of dollars playing video games. These players train for hours daily, maintaining reaction times measured in milliseconds, executing complex strategies under intense pressure. Some esports events fill stadiums, with millions more watching online, cheering for their favorite teams. Players develop repetitive strain injuries, hire nutritionists and sports psychologists, and retire in their 20s as reflexes slow. The infrastructure supporting esports rivals traditional sports, with coaches, analysts, broadcasters, and sponsors. This transformation of gaming into sport challenges our definitions of athleticism and competition, creating new forms of human excellence, measured in actions per minute and strategic depth. The relationship between computers and music extends beyond storage and playback to composition itself. Algorithmic composition dates back to Mozart's dice game for composing waltzes, but computers have elevated this to new levels. Modern AI can analyze thousands of songs to understand musical patterns, creating new compositions that feel authentic yet novel. Some artificial intelligence systems now collaborate with human musicians in real time, listening and responding like jazz musicians trading solos. The Shimon robot plays marimba alongside human performers, using computer vision to read their body language and machine learning to anticipate musical phrases. These collaborations blur the line between tool and partner, raising questions about creativity and authorship. When an AI helps compose a beautiful melody, who deserves credit for the creation? The programmer who wrote the algorithm, the musicians whose work trained it, or perhaps the AI itself? This philosophical puzzle becomes more pressing as artificial intelligence becomes more sophisticated, more creative, more seemingly conscious. The global positioning system that guides us relies on Einstein's theory of relativity to maintain accuracy. GPS satellites orbit at speeds and altitudes where time moves differently than on Earth's surface, running faster by about 38 microseconds per day due to gravitational time dilation and special relativity effects. Without correcting for these relativistic effects, GPS would accumulate errors of about 10 kilometers per day, making navigation impossible. This means every time you use GPS to find a restaurant or navigate home, you're conducting a practical experiment in Einstein's theories. The marriage of 20th century physics and 21st century technology happens invisibly in your pocket, space-time curvature translated into driving directions. Computer databases store much of human knowledge, yet they struggle with concepts children understand intuitively. The frame problem in artificial intelligence highlights how difficult it is for computers to understand what doesn't change when something else does. When you pick up a coffee cup, you know intuitively that the table doesn't move, the room doesn't change color, and gravity doesn't reverse. But computers must be explicitly programmed with these assumptions. This challenge reveals how much implicit knowledge we carry, how our brains efficiently model reality by knowing what to ignore. Every database query, every search result represents a small victory over this fundamental challenge. Computers learning to navigate the infinite complexity of information by focusing on what matters. The phenomenon of cryptocurrency has created entirely new forms of economic activity. People trade digital assets that exist only as entries in distributed ledgers, creating billions of dollars of value from mathematical consensus. Some individuals have become millionaires from forgotten hard drives containing Bitcoin wallets, while others have lost fortunes to forgotten passwords. One man in Wales has been trying for years to excavate a landfill to find a hard drive containing Bitcoin now worth hundreds of millions of dollars. These stories of digital treasure lost and found echo ancient tales of buried gold, except the treasure exists as magnetic fields on a disk, slowly corroding in garbage. The permanence and fragility of digital wealth creates a new kind of anxiety where a string of characters becomes more valuable than physical gold. Computer vision has progressed to the point where machines can describe scenes in natural language, creating poetry from pixels. These systems can look at a photograph and write captions like, "A lonely person walks along a misty beach at sunset," capturing not just objects, but mood and meaning. This capability emerges from neural networks trained on millions of image-text pairs, learning the relationship between visual features and human language. Yet these same systems can be fooled by adversarial examples, images tweaked in ways invisible to humans, but that cause AI to see guitars as turtles or stop signs as speed limits. This vulnerability reveals how differently computers and humans process visual information, how artificial vision remains alien despite its increasing sophistication. The Internet of Things promises a world where billions of devices communicate, from smart toasters to connected cars. Your refrigerator might order milk when supplies run low. Your thermostat might adjust based on your location. Your watch might call for help if you fall. This vision of ubiquitous computing brings convenience, but also complexity, as billions of devices become potential security vulnerabilities. A casino was once hacked through an internet-connected fish tank thermometer, demonstrating how the weakest link in security might be the most unexpected device. The challenge of securing billions of simple devices, many designed without security in mind, creates new frontiers in computer security where your light bulb might betray your passwords. Quantum encryption offers the promise of unbreakable communication based on the laws of physics rather than mathematical complexity. When quantum particles are entangled, measuring one instantly affects the other, regardless of distance, a phenomenon Einstein called spooky action at a distance. This quantum entanglement can be used to detect eavesdropping, as any observation of quantum states changes them. Banks and governments are beginning to use quantum key distribution for their most sensitive communications, trusting the universe itself to keep their secrets. The race between quantum computers that could break current encryption and quantum encryption that could restore security represents a new chapter in the eternal struggle between code makers and code breakers. Computer graphics have reached the point where virtual actors are indistinguishable from real ones. Digital doubles of actors can perform dangerous stunts or appear in scenes filmed after their death. Some actors now license their digital likenesses, creating a form of digital immortality where they can continue appearing in films long after retirement. The ethical questions multiply as technology improves. Who owns a person's digital likeness? Can actors be replaced entirely? What happens when we can't distinguish real from synthetic? These questions move from science fiction to courtroom as the technology becomes commercially viable. The development of machine translation has created bridges between languages, but also revealed the deep complexity of human communication. Early translation systems that converted word by word created humorous mistranslations, like translating out of sight, out of mind, to invisible, insane, when going through multiple languages. Modern neural machine translation learns from millions of examples, capturing not just words, but context, tone, and cultural nuances. Yet poetry, humor, and wordplay remain challenging, requiring understanding not just of language, but of human experience. Professional translators work alongside AI systems, using technology to handle routine translation, while humans provide the cultural understanding and creative interpretation that machines still lack. The carbon footprint of digital technology continues to grow as our appetite for computation increases. Training a single large AI model can emit as much carbon as 5 cars over their entire lifetimes. Streaming video accounts for 1% of global carbon emissions, equivalent to entire countries. Yet, the same technology enables remote work that reduces commuting, video conferences that replace flights, and smart grids that optimize energy use. This paradox of technology, simultaneously causing and solving environmental problems, defines our current moment. Data centers are increasingly powered by renewable energy, with some companies building solar and wind farms specifically to power their servers. The race to make computation carbon neutral drives innovation in both energy generation and computational efficiency. Computer simulations of the universe help us understand our cosmic origins. Supercomputers model billions of years of cosmic evolution, simulating how gravity pulls matter into galaxies, how stars form and die, how black holes grow. These simulations start with tiny quantum fluctuations in the early universe and evolve them forward in time, creating virtual universes we can compare to telescope observations. Each simulation requires months of computation on the world's fastest supercomputers, exploring different values for dark matter, dark energy, and the fundamental constants of physics. In a sense, we're creating pocket universes inside our computers, mathematical cosmos that help us understand our own. The similarities between simulated and observed universes raise philosophical questions about the nature of reality itself. The concept of digital death raises new questions about memory and mortality. Social media profiles of deceased users become digital memorials, frozen in time yet still receiving birthday wishes from friends who forget, or automated systems that don't know. Companies now offer digital estate planning, helping people decide what happens to their online presence after death. Some services use AI to create chatbots that can simulate conversations with the deceased, trained on their emails and messages. These digital ghosts raise ethical and emotional questions about grief, memory, and what it means to be gone in an age where our data persists indefinitely. The permanence of digital traces means we leave more extensive records than any generation before us. Yet, these records exist in formats that might become unreadable within decades. Computer-aided design has transformed how we create everything from buildings to molecules. Architects walk through virtual buildings before breaking ground, adjusting light and space in simulation. Engineers test thousands of variations of parts, optimizing for strength, weight, and cost without building physical prototypes. Drug designers use computers to model how molecules will interact with proteins, designing medicines at the molecular level. This ability to prototype in simulation accelerates innovation while reducing waste. The virtual becomes a rehearsal space for reality, where mistakes cost nothing but electricity. Modern airplanes, cars, and phones are designed entirely in computers before any physical prototype exists, born digital before becoming physical. The phenomenon of algorithmic recommendation shapes what billions of people read, watch, and buy. These systems analyze your past behavior to predict what you might enjoy, creating personalized experiences that feel almost telepathic. Yet these same systems can create filter bubbles, where you only see information that confirms your existing beliefs. The algorithms optimize for engagement, sometimes promoting controversial or sensational content because it generates stronger reactions. This invisible curation of reality affects elections, relationships, and mental health in ways we're only beginning to understand. The power to shape attention becomes a form of power over thought itself, raising questions about free will and manipulation in the age of artificial intelligence. The story of computer sound begins with simple beeps and evolves to three-dimensional audio that can place sounds anywhere in virtual space. Early computers could only produce square wave beeps, creating the distinctive 8-bit sound of vintage games. The development of digital audio allowed computers to record and reproduce any sound with perfect fidelity, transforming them into universal music machines. Modern spatial audio systems track your head movement, adjusting sound in real time to maintain the illusion that sounds come from specific locations in space. This technology enables virtual reality experiences where sound becomes as important as vision for creating believable worlds. The human brain processes audio faster than vision, making sound crucial for creating immediate emotional responses and a sense of presence. Distributed computing projects harness idle computer time from volunteers worldwide to solve complex problems. Projects like Folding at Home use spare processing power from millions of computers to simulate protein folding, helping researchers understand diseases and design drugs. SETI at Home analyzed radio signals from space, searching for signs of extraterrestrial intelligence. Using computing power donated by curious volunteers. These projects transform personal computers into nodes in planet-scale supercomputers, demonstrating how cooperation can achieve what no single organization could accomplish alone. During the early days of the pandemic, folding at home became the world's first exascale computer, achieving speeds of over 1 quintillion calculations per second as people worldwide donated their computer time to COVID research. The miniaturization of sensors has enabled computers to perceive the world in ways beyond human senses. Smartphones contain accelerometers that detect motion, magnetometers that sense magnetic fields, barometers that measure air pressure, and proximity sensors that detect nearby objects. These sensors work continuously, creating rich streams of data about your movement and environment. Apps use this sensor fusion to count your steps, detect falls, measure your heart rate through the camera, and even diagnose certain medical conditions. Your phone knows when you're walking, driving, or sleeping, building detailed models of your daily patterns. This sensory awareness transforms phones from communication devices into intimate observers of our lives, raising questions about privacy and the boundaries between helpful monitoring and surveillance. Computer memory hierarchies mirror the way human memory works, with fast but limited short-term storage and slower but vast long-term storage. CPU registers hold data for nanoseconds, cache memory for microseconds, RAM for milliseconds, and hard drives indefinitely. This hierarchy, invisible to users, orchestrates a complex dance of data movement, predicting what information will be needed next and staging it in faster memory. The principle of locality, which observes that recently accessed data is likely to be accessed again, underlies all modern computer architecture. This same principle appears in human cognition, where we keep recent thoughts readily accessible, while older memories require more effort to recall. The development of neural interfaces promises direct communication between brains and computers. Paralyzed patients can already control robotic arms with thought alone, typing messages and playing video games through brain implants. These systems read electrical signals from neurons, decode intended movements, and translate them into digital commands. The technology raises profound questions about identity and enhancement. If you control a robotic arm with your thoughts, is it part of you? Could we download skills directly to our brains, like learning kung fu in the Matrix? The boundary between human and machine blurs as we develop more intimate connections with our digital tools. Computer modeling of weather has become so sophisticated that meteorologists can predict the path of hurricanes days in advance, saving countless lives. These models divide the atmosphere into billions of cells, calculating how temperature, pressure, humidity, and wind interact according to the laws of physics. Supercomputers run multiple simulations with slightly different starting conditions, creating ensemble forecasts that show the range of possible futures. The butterfly effect limits prediction to about 2 weeks, after which tiny uncertainties amplify into completely different weather patterns. Yet within this window, modern forecasts achieve remarkable accuracy, turning the ancient dream of predicting weather into computational reality. The concept of digital scarcity, created artificially in a medium where perfect copies cost nothing, underlies entire industries. Digital rights management systems create artificial limitations on copying and sharing, enforcing scarcity in a post-scarcity medium. Non-fungible tokens, or NFTs, use blockchain technology to create unique digital items that can't be duplicated, bringing the concept of originality to digital art. These systems reveal the tension between the physical economy of scarcity and the digital economy of abundance. The ability to copy information perfectly and instantly could be humanity's greatest tool for sharing knowledge, yet we deliberately limit it to preserve economic models from the physical world. Computer forensics has become a crucial tool in law enforcement, revealing digital traces invisible to the naked eye. Deleted files often remain on hard drives, waiting to be overwritten. Metadata in photos can reveal when and where they were taken, sometimes even the serial number of the camera. Browser histories, search queries, and communication patterns paint detailed pictures of people's lives and intentions. Digital forensics experts become archaeologists of the recent past, reconstructing events from scattered bits of data. The permanence of digital evidence has changed how crimes are investigated and prosecuted, creating trails that are both easier to follow and harder to completely erase. The development of machine learning has revealed biases in human decision-making we didn't know existed. When AI systems trained on historical data reproduce discriminatory patterns, they hold up a mirror to society's prejudices. Hiring algorithms trained on past decisions perpetuate gender and racial biases. Facial recognition systems work less accurately on darker skin tones because they were trained primarily on lighter faces. These revelations have forced organizations to confront and correct biases they might not have recognized. The quest for fair AI has become a catalyst for examining human fairness, using mathematics to quantify and address inequality. Computer-generated imagery has reached the point where entire movies can be created without traditional filming. Virtual production techniques place actors in LED volumes, displaying computer-generated backgrounds that respond to camera movement in real time. This technology, used in productions like The Mandalorian, blurs the line between production and post-production, between filming and animation. Directors can change locations instantly, control weather and lighting perfectly, and create impossible worlds that actors can see and react to. The green screen, once the symbol of digital effects, gives way to immersive virtual sets that exist during filming, not just in post-production. The infrastructure of the internet continues to evolve in unexpected ways. Mesh networks allow devices to communicate directly without central infrastructure, creating resilient networks that can survive disasters. Satellite constellations promise to bring high-speed internet to every corner of the planet, connecting the billions still offline. Wi-Fi technology uses light bulbs to transmit data, turning illumination into communication. These developments promise to make internet access as ubiquitous as air, embedding connectivity into the fabric of civilization. Yet they also raise questions about digital divides, surveillance, and the environmental impact of launching thousands of satellites. Computer viruses have evolved from simple pranks to sophisticated weapons of economic warfare. Ransomware attacks encrypt victims' files, demanding payment in cryptocurrency for the decryption key. These attacks have shut down hospitals, fuel pipelines, and city governments, causing billions in damages. The attackers operate like businesses, with customer support helping victims pay ransoms and affiliate programs recruiting new criminals. This professionalization of cybercrime has created a shadow economy where stolen data and hacking tools are traded like commodities. The defenders and attackers engage in constant evolution, each side developing new techniques in an endless digital arms race. The phenomenon of social media has created new forms of human connection and isolation simultaneously. People maintain hundreds of digital friendships while reporting increased loneliness. The dopamine hit of likes and comments creates addictive patterns similar to gambling. Algorithms designed to maximize engagement accidentally optimize for outrage and division. Yet these same platforms enable marginalized communities to find each other, allow families separated by distance to stay connected, and give voice to those who might otherwise go unheard. The paradox of connection and isolation, of global reach and echo chambers, defines the social media age. As we near the end of our journey through these 100 fascinating computer facts, let's reflect on a few more wonders that showcase the profound impact of computing on our world. The development of blockchain technology has created new forms of trust that don't require central authorities. Instead of banks verifying transactions, mathematical consensus among thousands of computers creates an immutable record. This distributed trust enables not just cryptocurrencies, but supply chain tracking, digital identity verification, and smart contracts that execute automatically when conditions are met. The philosophical implications run deep, suggesting new forms of organization and governance that operate without traditional hierarchies. Computer modeling of proteins has recently achieved a breakthrough that had eluded scientists for 50 years. The AI system AlphaFold can predict how proteins fold into three-dimensional shapes based on their amino acid sequences, a problem so complex that it was thought to require centuries of computing time. This breakthrough accelerates drug discovery, helps us understand diseases, and might even enable us to design entirely new proteins for specific purposes. The solution came not from faster computers, but from better algorithms, showing that intelligence can substitute for brute force computation. The story of open source software represents one of humanity's most successful experiments in collaboration. Millions of programmers contribute code freely, creating software that runs most of the internet. Linux, started by a Finnish student in his dorm room, now powers everything from smartphones to supercomputers. Wikipedia, written by volunteers, has become humanity's largest encyclopedia. These projects demonstrate that people will work without direct payment when contributing to something meaningful, challenging traditional economic assumptions about motivation and value creation. Finally, consider the profound fact that computers have become extensions of our minds, augmenting our memory, perception, and reasoning. We no longer need to remember phone numbers, navigate by stars, or calculate in our heads. This cognitive offloading frees our brains for other tasks, but also makes us dependent on our digital tools. The boundary between what we know and what we can access has blurred. In a very real sense, losing your smartphone means losing part of your extended mind, containing memories, relationships, and capabilities you've come to rely upon. As we reach the gentle conclusion of our exploration, having wandered through 100 remarkable facts about computers and technology, I hope you found both fascination and tranquility in these digital tales. From wooden mice to quantum computers, from mercury delay lines to global neural networks, we've traced the extraordinary evolution of machines that have become our partners in thought and creativity. These stories remind us that behind every glowing screen, every silent calculation, every digital connection, there are human dreams, human struggles, and human triumphs. If this journey has brought you closer to peaceful sleep, or simply provided calm companionship in the quiet hours, please consider subscribing to join our community of curious dreamers. Your likes and shares help others discover these gentle explorations, creating ripples of tranquility across the digital landscape. And remember, whether you're drifting off to sleep now or still gently awake, these technological wonders will continue their silent work through the night, maintaining the invisible infrastructure of our connected world while you rest. May your dreams be filled with infinite possibilities, like computers calculating wonders in the darkness. May you wake refreshed, ready to engage with the remarkable tools that augment and amplify human potential. And may you always remember that behind the cold precision of silicon and electricity beats the warm heart of human creativity, the same spark that led our ancestors to paint on cave walls, now painting pixels on screens. Sleep well, dear friend, knowing that you are part of the most remarkable technological transformation in human history, a participant in the great digital dream we're all creating together. Sweet dreams and peaceful rest.